was the artificial methodologies or someone the artificial methodologies for solving some of the problems that you're going to be solving in this class that might not have a initial basic feasible solution when you're trying to apply the simplex method. So there are two methods that we can use to actually get that first basic feasible solution in order to apply the simplex method. The first method that we discussed is called the M method, and the second method that we started discussing on Tuesday was the two-phase method. So we covered the first portion of the two-phase method in class, but just to recap on what we did and what we explained on Tuesday, the two-phase method eliminates the use of the constant m. Remember, for the m method, we were using a constant m that was representing a large number. And we explained how the use of that constant help you to get the initial solution that you need to apply the simplex method. But this method, the two-phase method, eliminates the use of that constant. The method solves the LP in two phases, and that's where the name of the method comes from. The phase one attempts to find a starting basic feasible solution, and if one is found, then we proceed to phase two to solve the original problem. So in this table, I have the summary of the two-phase method, but if you remember, the main difference between this method and the M method was that instead of solving an objective function in which you were using these M constants, now you're going to be minimizing in your objective function the summation of the values of the artificial variables. So here's an example. So we started discussing the case for a minimization problem. We have three constraints. One of them is an equality. So once you see an equality, you're going to be able to understand that at that point you're going to need an artificial variable, because you're not going to be able to add a slack variable or an excess variable. So right there, you know that you're going to be needing this artificial variable to solve the problem using the simplex method. We have two constraints. One of them is a greater or equal constraint, and the other one is a less than or equal constraint. So if we want to put this problem into a standard form, this is how it's going to look like. So we have an excess variable. We have an excess variable here for the second constraint and a slack variable here. In phase one, the attempt is to find a starting basic feasible solution for the original problem. So now we're going to replace the original objective function c, regardless of whether you are minimizing or maximizing in the original problem, with a minimization problem of the summation of the artificial variables, which are represented by r. R equals the sum of the artificial variables, and solving this new minimization problem, this is our new objective function. So we're going to minimize the summation of all the artificial variables that you're going to need to set up your basic feasible solution for using the simplex method. So this is how the phase one in standard form is going to look like for this problem, this example. So remember, for our first constraint, we had an equality. We cannot use a slack variable or an excess variable, so we add an artificial variable. The goal again is to get a basic feasible solution in the simplex tableau. We know this is a negative variable, so that cannot be used as a basic feasible solution. So that's why we also add an artificial variable to our second constraint. But for the third constraint, we have a slack variable this slack is a positive variable, so that can be part of our basic feasible solution. So now we have two artificial variables as part of our problem. And as I mentioned earlier, the objective function for the first phase is going to be the summation, the minimization of the summations of the artificial variables, R1 and R2. From this problem, from phase 1 of the problem, we can get the starting basic solution. Now we know that we're going to have R1, R2, and S1 as our basic solution. And the values for those variables are 3, 6, and 4, which are the right-hand side of the constraints. Any questions up to this point? Okay, so today we're going to have a lab that is going to be looking at a problem for the two-phase method. So try to ask questions if you still have some doubts. So we have our problem for the phase 1. We can set up the tableau. Again, we're going to have R1, R2, and S1 as our basic feasible solution. So R1, R2, and S1 are going to be part of our tableau for the first 3 rows. Row 0 is the objective function row, and we basically take the parameters from the phase 1 formulation, and we put them into the tableau. Now the problem is R1 and R2 are part of our basic solution, but we see that in the tableau those two variables are not 0 in the objective function. So in order to proceed with the phase 1 iterations of the simplex method, first we need to make those two values 0. So before proceeding with the simplex method's computations, the R row must be made consistent with the rest of the tableau. Okay, so R1 and R2 are substituted out in the R row by using the following row operation. So you're going to use the Gauss-Jordan method to make those two parameters or constants 0. And this is how you proceed. So once you apply the Gauss-Jordan operations, the Gauss-Jordan method, this is how the tableau should look like. So now you have your basic solution, the basic feasible solution, and row 0 represents the 0 coefficients here. That basically tells you that these variables are part of your basic feasible solution. So now you have R1 equals 3, R2 equals 6, and S1 equals 4. At this point, then, we are able to apply the simplex method because the tableau is in the form that we need in order to proceed with the simplex method. So we're going to apply the simplex method now. This is a minimization problem. So we're going to look at the largest positive value, and that is going to tell us which variable is going to enter the solution. So right now 7 is the largest positive number, so that tells us x1 is going to enter the solution. So x1 is going to remove one of these 3 variables, and it's going to become part of the basic feasible solution. Now the problem is to determine which of these 3 variables is going to leave the basic solution. And for that, we know that we can use the minimum ratio method, which is what we are doing in this column, to find the minimum value. So we know x1 is going to enter the solution. So we're going to pivot one of these values or coefficients in this column. Actually, one of these 3. So we need to find out which one is going to be our pivot. So we're going to divide this right hand side by this value, and that's going to give you the ratio. Same thing here. We divide 4 divided by 6. I'm sorry, the other way around. 6 divided by 4, that's 1.5. And 4 divided by 1, that's 4. So from these three, we find the minimum. The minimum equals 1. So that is telling us that R1 is the variable that is going to leave the basic solution. And we're going to pivot this coefficient, which is in the first row of our tableau. So this is something that you already know. So we're going to pivot 3, and once we perform simplex method operations, this is how the tableau is going to look like. So now x1 is part of our basic solution. R2 and x1 were part of the tableau at the beginning, so those stays the same. But now you're going to have different coefficient values here because you applied the simplex steps to make this value 1 and to make this value 0, which is what we observed here. And then you repeat the process. You find the largest positive value from the objective function row. That's going to be x2. So x2 is going to enter the solution. And then you're going to find the value or the variable that is going to leave the solution using the minimum ratios. And you find the minimum, and you repeat the process until you get to this point. So anyone remember what will be the coefficient or the value that is going to tell you that you are done with the first phase of the two-phase method? What we are searching for to determine that we are done with the first phase? You can look at your notes if you want. So what we are trying to do in order to determine that we got until the last tableau of the first phase is to find the minimum objective function, and then objective function value needs to be equal to 0. So if we find the objective value function, you know it went from 9, 2, and then 0, that's telling us that you got the simplex first phase optimal tableau. Also, you're going to notice that the artificial variables are no longer part of the basic solution. So they are not part of these groups. Any questions so far? So what we have done is just changing the objective function. Instead of having the original objective function, now we have the minimization of the summation of the artificial variables. We know that we're going to have some artificial variables because we had a constraint type of equation which will not allow you to use one of the variables as your basic solution for the first tableau. And we also had a greater or equal constraint that will not allow you to use one of the variables as your basic solution. So those were the two cases in this particular example. So we got into this point. This is our phase 1 optimal solution. So now let's proceed with the phase 2. So the new arrow is used to solve phase 1 of the problem, which yields the optimal tableau, which is represented here in this tableau. Because the minimum R equals 0, phase 1 produces the basic feasible solution. X1 equals 3 over 5, X2 equals 6 over 5, and X1 equals 1, which is again coming from the optimal tableau, right-hand side. So if you look at these values, the right-hand side, that's telling you the values of the basic variables. At this point, the artificial variables have completed their mission, and we can eliminate their columns altogether from the tableau and move on to phase 2. So we're going to eliminate these columns, and we're going to use the rest of the information for phase 2 of the method. Okay, so phase 2, we go back to our original objective function. So now we're going to have the minimization of 4x1 plus x2. That's our original objective function. We are no longer minimizing the summation of the artificial variables. But something that you need to notice now is that our constraints are not the original constraints. Our constraints are coming from this optimal tableau from phase 1. So the coefficients of the variables for each constraint are going to come from the optimal tableau of phase 1. So for instance, our first constraint is going to have x1 plus 1 over 5 e1 equals 3 over 5. Okay? And the same thing you do for the second constraint and the third constraint. Any doubts about that? So you found the optimal solution for the phase 1. The coefficients of that tableau are going to be used to find the constraints for phase 2. The objective function, however, the objective function is coming from the original formulation. Okay, so those are details that you need to remember. Phase 1 has transformed the original constraint equations in a manner that provides a starting basic feasible solution for the problem. Okay, so the tableau associated with phase 2 problem is thus given by this new problem, this new formulation, and we can set up that tableau using those coefficients. So remember, from here we have our basic variables are x1, x2, and s1. So let me make that again. So we have x1, x2, and s1. And the reason why is because those are the ones that have the coefficients equal 1 and in one of the rows and 0 in the other ones. But as you can notice now, for the objective function row, we have the same problem that we found on the phase 1, which is you have some basic variables that are part of your basic solution, but they still have some coefficients that are not 0 in row 0. So what do? You can just read from here. Basically, what you're going to do is, because the basic variable x1 and x2 have non-zero coefficients in the 0, they must be substituted out using the following operation, which is what you did for phase 1. You need to make sure that for those basic variables, the values of the row 0, this value and this value needs to be equal to 0. Do you have any questions? So you're going to be using this Gauss-Jordan method one more time for the row operation. So you're going to make the new 0 for those coefficients that are part of your basic solution. You need to make those equal to 0. So once you perform those operations, this is how the tableau looks like. So this is x1, x2, and s1. And now you can proceed with the simplex method. So now after all this process, once you apply the simplex method to this tableau, you're going to find the optimal solution of your problem. But once you perform all those operations and you get to this point, then you're sure that you're going to get a solution. So because we are minimizing the original problem, Then we know that we're going to look at the largest positive value on row 0. So that makes a E1 candidate for entering the basic solution. So E1 is going to enter the solution. And then we need to find the variable from these three that is going to leave the solution. So you're going to use the ratio to find out which of the variables is going to leave the solution. So the removal of the artificial variables and their columns at the end of phase 1 can take place only when they are all non-basic. So if one or more artificial variables are basic at 0 level, then the removal requires the following additional steps. So we are talking one more time about phase 1. Let me go back and show you this. So basically what we are saying is we can delete these two columns from here because R1 and R2 are no part of the basic solution. So at that point you can tell, okay, we don't need this anymore. We can remove that. But that's not always the case. And that's why we are referring to these extra steps. So in the case that you found your optimal solution for the phase 1, but you still have an artificial variable as part of your solution, then you need to follow these two steps. Basically what you do is you select a 0 artificial variable to leave the basic solution and designate its rows as a pivot row. Then the entering variable can be any non-basic, a non-artificial variable with a non-zero, positive or negative value in the pivot row, and then you perform the simplex iteration. Once you are able to remove the artificial variable then from the basic solution, then you can basically remove the columns and proceed with phase 2. And we're going to see that case in our lab in a couple of minutes. So the lab is, I'm going to tell you, this is the first time that you're going to be solving a problem using the two-phase method. It's going to be kind of difficult, I would tell, but I'll be here to help you out. I just want you to go through the process of practicing this method. So that basically concludes the lecture. Now we're going to have some time to practice this method using the lab. So please, I know there are some of you who are missing, so please find at least one person to work with so you can basically share some of the information in this lab. And let's try to work on that in this problem. So let's see. For the purpose of the video, let me show you the lab. So instead of having a minimization problem, now we're going to have a maximization problem. This is lab number 7. So we have 3 variables, 2 constraints. One of them is a less than or equal constraint, which basically tells you from the start that you're going to need an artificial variable to get your basic solution. So you're going to have one artificial variable for this constraint, which is the first constraint. The second constraint is a greater or equal constraint. I'm sorry, the other way around. So for the first constraint, you're going to need a slab variable. For the second constraint, which is a greater or equal constraint, you're going to need an artificial variable to get your first basic solution. So the lab, I tried to make it so you can follow step by step what you need to do. So the first thing that I ask you to do is to put the problem in equation form and add the necessary artificial variables. and then formulate the problem for phase 1. So to formulate the problem for phase 1, you know you're going to add the artificial variables, and then you're going to change your objective function. Instead of having the original objective function, you're going to have the minimization of the summation of the artificial variable. In this case, one more time, you only have one artificial variable, which is for the second constraint. So you're going to be minimizing that artificial variable by itself because it's just one artificial variable. So then part B, I give you the tableaus. So show that phase 1 will terminate with an artificial basic variable at 0 level. You may use your calculator or Excel for convenience solving the tableaus. So I'm pretty sure for this first phase, you're going to have integer numbers, integer values, so it's going to be easy for you to get the row operations. But that's not the case for the second phase, so you might need to use a calculator or a Excel to find out the values for the second phase. So I'm giving you the tableaus. I think you're only going to need the tableaus that I'm providing. If you need more than that, just check with me to see if you're following the right steps and you're on the right track. Then we get to, so once you find the optimal solution for the first phase, we get to the second phase, which is remove the 0 artificial variables prior to start of phase 2. So you're going to remove those artificial variables here, and then you're going to have some extra tables to work on phase 2. The last thing that I asked you to do is to provide me with the objective function and the values of the variable. This is something that you do if you want. If you want to double check that you get the right answer before submitting, you can use Excel to check your solution. So you can use the solver in Excel to find the solution of the problem and find out if you got the right answer. Okay, so let me pass the lab. Okay, so let's set up the first portion of the lab. So part A, you need to set up or formulate the problem for phase 1. So one thing that you need to remember is phase 1, the objective function for phase 1 will always be the minimization of the summation of the artificial variables. Independently of the original objective function, phase 1 the objective function for phase 1 will always be a minimization problem. So you're going to have the minimization of the objective function. I'm going to leave that to the end. Subject to, we need to put these in equation form. So we have 2x1 plus x2 plus x3 plus s1 equal to 2. Then we have 3x1 plus 4x2 plus 2x3 plus the artificial variable that I'm calling R2 equals 8. And then we have x1, x2, x3, s1, and R2 greater or equal to 0.
Don't you want to add the x there?
I'm sorry, yes, you're right. So you have minus E2. So you're right, you have your minus x2. Yes. Yes, and that's up to you. You can use E1, you can use any identifier as long as you have a unique identifier for each variable. Okay? So I'm using 2 and 2 here because it's part of the second constraint. That's a good question. Excuse me? You're minimizing this summation, all the R's. But in this case, we only have one. So you just minimize that only variable.
I mean, the left side where it says, there's no knowledge product at the bottom. I'm just wondering.
Doesn't matter. No. Okay, so let's set up the first tableau for this problem for phase 1. So our basic variables at this point are S1 and R2. So we have in row 0 we have 0, 0, 0, 0, 0, minus 1, and 0. Then for the first constraint, we have 2, 1, 1, 1, 0, 0, 2. And for the second constraint, we have 3, 4, 2, 0, minus 1, 1, and 8. So the first thing that you have to do here is you notice that R2 is part of your basic solution, but row 0 does not represent that. So you need to make that minus 1 in this part of the tableau. You need to make that number 0 in order for R2 to be part of your basic solution. So what do? You need to perform some operations, some row operations to make that number equal to 0. So what you can do is just multiply this row times 1 and add that to row 0. So once you do that, then you will get S1 one more time, R2. You get 3, 4, 2, 0, minus 1, 0, 8. You get 2, 1, 1, 1, 0, 0, 2, and then 3, 4, 2, 0, minus 1, 1, and 8. So at that point, you have your tableaus ready. So you have your basic variables. They are represented in the right format. So what you do now, what's the next step? you need to enter, you need to search for this minimization problem. So you search the first row to see if you have any positive coefficients. You do have some of them. You basically decide to get x2 because it's the largest one. So you know x2 is going to enter your solution. So this is your pivot column. Now you need to find out which one is the variable that is going to leave the solution. So you're going to perform that minimum ratio test using this column and using this column. So you get 2 over 1 divided equals 2, and then you get 8 divided by 4, this equals 2. So now you need to make a decision because the ratio test, the minimum value, both of them are 2. So you need to decide which one you want to enter. In this specific problem, what we're trying to do in phase 1 is to basically eliminate the artificial variables from our solution. So my recommendation is to take this row and pivot this number. If you do that, then you're going to enter x2 and you're going to get r2 out of the solution. That should give you your optimal tableau for phase 2. But the purpose of the exercise, at least for teaching purposes, is to show you the things that can happen if you go the other way around. So let's say in my solution, I'm gonna decide to enter x2 and x1 is gonna leave the tableau. You don't have to do this, I just want to show you something. So in my solution, this is gonna involve some extra steps. I'm gonna have the ratio, so r, x2, r2, then I'm gonna have minus 5, 0, minus 2, minus 4, minus 1, 0, 0, 2, 1, 1, 1, 0, 0, 2, minus 5, 0, minus 2, minus 4, minus 1, 1, and 0. Okay, so again, my recommendation always is to try to get these artificial variables out first, and that is possible here. But I went the other way around to show you something. So now you get this tableau. You still have your artificial variable in your solution, but if you search row 0, the tableau is optimal. So you got an optimal tableau. The right-hand side is 0. Got an optimal tableau, but the artificial variable is still there. So again, I want to show you what you do in those cases. So if we go back to this part of the lecture, these are the steps that you follow for such cases. So in the case, if one or more artificial variables are basic at 0 level, then the removal requires the following additional steps. And very basic steps, you're going to select a 0 artificial variable to leave the basic solution and designate this row as the pivot row. So you're going to look at the row 0 and you're going to choose one of the variables from the 0 row that has a value of 0, and you're going to choose one of them. It can be any non-basic and non-artificial variable with a non-zero, positive or negative coefficient in the pivot row. And then perform the associated simplex iterations. So what I'm going to do is to show you that. Again, if you go the other way around, you don't have to perform these extra steps. At the end, you should get the same solution. So I'm going to remove the 0 artificial variable prior to the start of the phase 2. So referring back to this. So this is my tableau. So I have -5, 0, -2, -4, -1, 0, 0, x2, 2, 1, 1, 1, 0, 0, 2, then R2, -5, 0, -2, -4, -1, 1, and 0. So this is the same information that I got from the previous tableau. Now I'm going to choose one of these variables, non-artificial variables with any coefficient, positive or negative, to enter my solution. So I'm going to choose this one, x1. So this is going to be my pivot column. And obviously, if I'm trying to get R2 out of the solution, this is going to be my pivot coefficient. So this is decided based on the extra steps that we just discussed. And then I'm going to pivot this because I want to take R2 out of the solution. So once you perform those steps, you're going to make x1 part of your solution, x2 and x1. This is going to be -2. I'm sorry, this is going to be 0, 0, 0, 0, 0, -1, 0, 0, 1, 1 over 5, -3 over 5, -2 over 5, 2 over 5, and 2. This is 1, 0, 2 over 5, 4 over 5, 1 over 5, -1 over 5, and 0. So again, what you're doing is you're going to multiply this times -1 over 5. You're going to make this 1, and then you're going to make this 2, 0. So this is how the tableau should look like after those operations. And now you have all your coefficients 0, right-hand side equals 0. The artificial variable is out of the solution. So this is your tableau for phase 2. And that should be the same that you have without the. So now you're going to take this tableau, you're going to drop R2, this column, out of the tableau. You're going to use these coefficients for your phase 2, and you're going to refer back to the original objective function. So if you, let me set that tableau for you. So for phase 2, we're going to have these same coefficients here are going to be part of these two rows. So you have x2 and x1. So you're going to have the same coefficients, 0, 1, 1 over 5, -3 over 5, -2 over 5, 2 over 5, 2. Then you have 1, 0, 2 over 5, 4 over 5, 1 over 5, -1 over 5, and 0. But the objective function, now you go back to the original objective function. So that objective function was -2, -2, -4, 0, 0, and 0. So your basic variables at this point are this one and this one. So before you apply the simplex method, then you need to make these two coefficients 0. So you have to perform those row operations one more time, make them 0. And then at that point, you just apply the simplex method, and you get the optimal solution. And that's your solution for the problem. Okay, so at this point, then you should know what to do to complete the problem. So if you make those 0, yeah, I'm gonna let you work on that. I'm being helping you too much, so let's do the rest of the work independently. Now you can use Excel or a calculator to get the values for those fractions.
Is that how you did that with Excel?
I did it with a calculator, actually.
I just don't know where you're getting a fifth from.
You can
Like
check
when you
here.
divide it through by a fifth.
So this is just
right there.
This is for the phase 1. Are you working on phase 2 already, or? Because this is phase 2.
But that's where the fifth comes from, is dividing it all the way through by this, which we don't have.
Yeah, so you multiply this minus 1 over 5, and you get 1 over 5, and so on. So my guess is instead of adding this, instead of taking this out of the solution, if you take this one, then you should be able to get this same value.
So turn that into a 0, you just added this row up.
Oh no, that's not true, because you're gonna have then S1 and X and X2. Yeah, so your numbers will be different, but at the end you should get the same solution. Because you have a different initial value, have an initial basic solution that is different.